One more example. Here we have glucose is burned in a bomb calorimeter. A bomb calorimeter is a constant volume calorimeter. The calorimeter has a heat capacity of 641 joule per Kelvin. When this much glucose is burned, the temperature of the calorimeter increases by 7.793. So if one considers the chemical reaction as the system, what is the sign of Q? All right, what is the sign of Q? Well, let's draw a picture here. Here's our calorimeter. Okay, so calorimeter. And maybe you remember from introductory chemistry, we used like a coffee cup calorimeter. Essentially, this is insulated, so no heat can go outside the calorimeter, and is a constant volume, so this is also rigid, so there's no possibility of PV work. Remember, work is minus the integral of P dV, and if it's rigid, that means constant volume, a bomb calorimeter is rigid. This implies dV is equal to 0, which implies work is equal to 0. So there's no work. So essentially there's a little mini universe in which heat can go from one place to another. And our system, as we suggested in the problem, our system was a chemical reaction, C6H12O6, that's glucose, and we're going to burn that in water, or sorry, in oxygen, to produce, let's see, 6H2O, 6CO2, and that's 6, 12, 18, 6, 12, divided by 6, 6. There's a balanced chemical equation. All right, so there is our system. Our system is the chemical reaction. All right, so that's abstracted out. And then the calorimeter, typically you have water in a calorimeter and something like that. But here, delta T, given an example, delta T is a positive number. Delta T for the calorimeter, 7.793. So delta T in here, in the calorimeter, the temperature went up. What does that mean? For the temperature to go up, Q must have gone from the chemical reaction into the surroundings, into the calorimeter, in order to increase the temperature of the calorimeter. So if Q is lost from the system, this means that Q, and we're considering the chemical reaction as a system, Q is less than 0. Okay. And calculate Q for the reaction. Okay. Let's do that. So Q for the reaction is equal to minus Q of the calorimeter. Why is that? Again, it's like a first law argument. This is a mini universe isolated from anything else. And so any energy changes here, if Q is lost here in the system, it has to be picked up here in the surroundings, which are isolated from anything else. So the heat lost here is equal to heat gained there. First law argument. So Q reaction is minus Q calorimeter. How do you calculate Q calorimeter? We know the heat capacity, 641 joule per Kelvin, minus 641 joule per Kelvin. That's a heat capacity, not a specific heat. It's just joule per Kelvin. And let's look at delta T, final minus initial. Well, it's already given, 7.793. And that is in degree C. That's also in Kelvin. Let's write it in Kelvin this time so things cancel out. So we calculate this out, and we get 5.0 times 10 to the third joule with a minus sign. Keep forgetting that minus sign there. With a minus sign. Minus sign carries over. This is a positive number. So the energy or the heat transferred in the reaction is minus 5.0 times 10 to the third. Note that here Q is less than 0 for the reaction. This implies that the reaction is exothermic. In other words, the surroundings heat up. That's just what we have here. It's exothermic. The surrounded heated up. It heated up by 7.793 delta T. Okay, so in summary, we have now a couple ways to calculate work done going from an initial state to a final state, or heat transferred going from initial to final state.